Hi everyone. Let me just admit everybody, and then we'll be able to start in just a sec. Hi.
Hello.
How are you?
Doing well. I'm awake.
I hear you. Just a sec. Okay. Good.
Oh yeah, on the homework, can we, if we don't know how to solve one of the questions, can we just put down like a question mark and will we lose points for that?
So that's a great question. I think I'm going to answer you in two different ways. Give me just a second. So today, our what we're going to cover is chapter 2.5. That covers all the material for what's due for the homework, right, which is due by midnight, and then also what's on the quiz, okay, which we'll start. We'll talk about that at the beginning of class as soon as everybody's here. And then so what we're going to do today, 2.5, isn't as long of a chapter as what we've been covering so far. So we may actually have some extra time at the end of class, right? And what I would like to do is open it up to you guys. You can think about it at the end. Give me a sec. Think about it at the end and answer me then. I can do some question and answer session at the end of class about our homework problems, okay? So if you guys have questions about that, and then you can also come back to office hours this afternoon and we can work through that, okay? And then I would say ask those questions that you have question marks on at that point, like at the end of class today, and then also in office hours today, because you want to get those answered, because the homework problems are going to be a good set to learn the material to prep you for the quiz. Let's say you don't get a chance to answer all the questions that you have all these question marks. I would say pass it in. I'm going to circle it, right? So you'll get like points off for not completing it, okay? But then you can resubmit that homework next week, okay, to get those points back, okay? So the homework is always a place where even if you leave it blank, right, you'll lose points initially, but then you can get a chance to get those points back. And you will want to do those homework problems because they all of them are nicely selected actually to help you figure out like what to do for stuff. Does that answer your question?
Yep, that makes sense. Thank you very much.
Yep. All right. I think we've got everybody here. So, so first off, I wanted to talk about. I saw my chat window. I guess kind of disappeared at some point during the lecture. I have a hard time. I've got a lot of windows up on the screen, and I need to be able to see what's going on. But in the lecture notes yesterday, you guys asked a lot of questions, and somebody asked it later, I think, in office hours too. And I wanted to point out example 7. Right, I said I was working through it and I said, oh, this is the probability of B alone and probability of A alone. And normally you guys were asking this question, which is, I thought probability of B was that whole circle. So how did I know it was B alone? And the reason I know is because this was a typo, and it should have said the probability of B alone and the probability of A alone, which is that little, we've got that joint, kind of football shaped circle here taken out of it. So it's just this partial circle, okay? That's why it was a typo. I forgot to put it in. I'm copying these lecture note examples down from my notes so that you guys can have them. And it's something that I forgot to type in. So that's how I know it was B alone, because obviously I knew it because I'm looking at my notes. But you guys didn't know it because it wasn't there. Okay, so it should have been there. That's example 7 from yesterday's lecture notes. And you'll see this if you look up online when I scan these in, I post them, you'll see the trying to fix the typos. But if you notice any other typos and stuff too, you can stop me during the lecture and like sometimes I can't always see the chat window, but you can like unmute yourself and then say, hey, wait a minute, I've got a quick question on that. How come it says be alone or whatever, and then we'll fix it. Okay, so a couple things, administrative stuff. So we have homework due today. That'll be due by midnight tonight, Eastern Standard Time. And what you'll want to do is upload, like you've been working on these examples, these homework problems, maybe on a separate sheet of paper, maybe you've printed out the homework questions and you worked on them there. You'll want to scan them in or take a picture. Send it to me as a PDF, please. I have a really hard time reading files that are not PDF. I can do JPEG, but I can't write comments on it very easily, so it won't be as helpful for you. if you give me a PDF, I can, circle things more easily and kind of give you a grade more easily on that. So you'll want to be able to upload those. If you have trouble uploading them for whatever reason tonight, send me an email, like, somehow your internet was going weird or whatever, it didn't work. Send me an email so I can get them, and then we'll talk about how you could upload, because we want those copies there because it's easier for me to give you feedback on stuff what's missing. I'll put the grades in. I'll work on those this weekend. The quiz today, I'm going to put out an announcement on this too. So if you're not quite getting what I'm saying, then I'll put out the announcement later today to talk about how you're going to take the quiz. The quiz is going to become available today, like this afternoon. I still haven't decided. We can talk at the end of class if we want it to be, 3 o'clock Eastern time or 4 o'clock Eastern time. Either way is fine. And what will happen is it'll become available for a 24-hour window. This is to accommodate different time zones. But you guys should know that when you start taking the quiz, like you'll go into Blackboard, I think it's there under assignments maybe, or I know I can see it on gradebook and I can see it on assignments, but I think if you go under assignments, it's there. When you start to take the quiz, then the timer will start, okay? And then when the timer starts, you'll have 45 minutes to take the quiz, okay? Plus 15 minutes to upload your answers. The 15 minutes is a restriction that my department has put out. We only can do 15 minutes for uploading stuff. So you guys will have an hour total to take the quiz, okay? And then which includes the time to upload. And you'll want to do the same thing like you did for the homework, which is scan it in or take a picture, but please give me a PDF so I can grade it more easily. And then we'll do that. If you have any problems, I'll be online, for a little bit this afternoon, kind of intermittently through the evening, and then intermittently tomorrow. So you can email me, and certainly if you see a typo, you can let me know, and then I'll try to fix it. I think that's about it. I'll put that protocol up in the announcements today, like after class or after office hours, so you guys will have a feeling for like how that works. I know you guys are all at home, or we're not in a classroom like normally we'd be taking this in a classroom. And so I'm going to trust you that you're not talking to each other or talking to other students about how do you solve a given problem. We do assume that it is open book, open notes, okay, so that you are free to look at your notes, your homework problems, your classwork, things that you've been working on. That's fine. I'm also going to ask you not to look at things like on Wolfram Alpha or whatever those online math solver problems are, because we do want to kind of get a gauge for how much do you know this material. And then yeah, so open notes, open books is not cheating because I'm assuming that it is, right? But talking to each other, looking things up online, I would consider that, not quite honest in terms of you taking the quiz yourself, okay? So with that said, unless anybody has any questions, I think, like I said just a minute ago, when we finish chapter 2.5, I think we'll have some time at the end, and then I'll open it up to question and answer. We can talk about homework problems. I think the homework problems are a good way to study for the quizzes and the tests. So if you guys have questions on how do you solve a given problem, or what does this mean, or did I do this right, it doesn't make sense, you can ask it at the end of class today, or you can come to office hours and we can also talk about it then too. All right, I think that's enough administrative.
How many questions is the quiz going to be?
I think, let's see, I was just looking at this one. I think there are like maybe 4 or 5 questions, but they have multiple questions on them. I think that they're probably on par difficulty with maybe like homework problems, okay? So, so you do have to think, you kind of have to work things through, you have to bring together the stuff that we've been talking about, and then make it work, yeah. Okay, but you should be able to take it within the 45-minute time period, okay?
Okay, thank you.
Yep. All right, so today we're going to be talking about independence. Let's see if I can get this straight here. All right, so this is chapter 2.5. Okay, so independence is a really important concept, and we're going to be using the idea of independent events, especially when we talk about statistical analysis later on the second part of the class. And it's different than like when we talked yesterday about conditional probability, which was about dependent events. Like if I flip a coin and I get a heads, I go to this bucket. If I get a tails, I go to that bucket. So going to which bucket is going to be dependent on the outcome of that coin toss. Can we talk about independence now? We're talking about events that are happening, and the event that's happening now is completely unrelated to the event that happened just before it, and the events that happen afterwards are unrelated to the event that's happening now. So the probability of this event here doesn't rely on the probability of any of the events preceding it, okay, or any of the events that are happening around it. And that's an important concept because we need to know in statistics that the events themselves underlying our statistical analysis are going to be independent, okay? On a couple definitions, then we'll jump right in. Hang on a second. I'm gonna let people in. Let's see. Okay. So let me write down the definition and then we'll go into examples and stuff. So let's say in independence, we've got two events, and we'll start off with two events and then we'll extend this out to other events too. But two events, A and B. Now these two events are within our same sample set. Okay, so we're asking a particular problem, a particular question, we're having people answer it, but these people don't know each other, so their responses are independent. Say for example, A and B, oops, are independent. If the fact okay, so independence, let's see, make sure that that's in focus here, I think. Okay, so two events A and B within our sample set are considered independent, right, if the fact that A occurs does not affect the probability of B occurring at all. Okay, so A happens, B happens, okay, that they don't influence each other, but they do happen, say, within the same given experiment. So we can think about this in terms of like, I'm going to roll a die, a six-sided die, and I'm going to get a six, right? Say, for example, I take a die and I roll it and I get a six as if they slide up. Then I roll it again, or I roll a second die. Okay, so I roll a six, I roll one die, I get a six, I roll another die, and I get a three. Those two die, right, the outcome of one die isn't affecting the other, okay? And it's the nature of the experiment. I'm not saying when I get a six, I need to roll this special die over here that's going to do something different, okay? So I'm just going to roll a die, I'm going to roll another die, and I'm going to get two independent outcomes. Okay, so that means that when we say, in terms of intersections and unions and how we describe stuff, the probability of A and intersect B is equal to the probability of A times the probability of B. And I'm going to put a box around that and a couple stars. Okay, it's a really important formula. It's a formula that you're going to be using a lot, right? Because we're going to tell you at some point, you know, these events are independent, and it's going to allow you to use this particular formula here. Okay, so let's think about kind of the stuff that we did yesterday with the conditional probability. Right, remember our conditional probability said we have the probability of A given B, right? So that means that, you know, I want to find out, like, what's the probability of A happening given that B has already happened. So A was dependent on B, right? This is a conditional probability. And that's equal to the probability of A intersect B. So they both have to occur divided by the probability of B, right? So we have to know, because that's a subset, B is happening, and then because once B has happened, then A is going to happen. So A can only happen if B has happened, right? So here, you can imagine if I were to substitute in, right, this is going to be the probability of A times the probability of B divided by the probability of B. If they're independent, it's just going to be the probability of A. Right? So if A and B are independent, right, this whole given conditional probability breaks down, right? A isn't dependent on B at all. If the probability of A given B, but they're independent from each other, it's just the probability of A, okay? Which is just probability of A. Okay, so let's think, I'll write that down. Okay, if they're independent, probability of A given B is just the probability of A, okay? But we're going to say our intersection, probability of A times the probability of B. Okay, so I'm going to take out my lecture examples for chapter 2.5. Okay, we're going to start working through some things. So I've got my first example. A coin is flipped and a die is rolled. Okay, so we want to find the probability of getting a head on the coin, getting a head on a coin and a 4 on the die. Now, let's take a step back before I jump into this problem. Remember, yesterday we said, okay, if a coin is flipped, depending on the outcome of that coin toss, we're going to do one thing or the other, okay? But in this case, I'm rolling a die and I'm flipping a coin, and I'm just recording the results. Okay, so you can see how the outcome of each one is not influencing the other, okay? So in this case, right, we want to find out the probability of getting a head on the coin and a 4 on the die. So these two events are going to be happening. I'm looking for that outcome, okay? But they're not influencing each other as they're happening. So I'm just going to write down the sample spaces so I can see it, because I want to spell it out for you what it's been looking like. So sample space.
I had a question.
Yeah.
What is the difference between what we're learning right now and what we learned in like 2.2?
Mutual exclusion?
Yes.
Yeah, that's a great question. So mutual exclusion, remember, let's see, where can I write? So we're going to actually talk about mutual exclusion in just a minute, but I'll write it down. So with mutual exclusion, right, when we have mutual exclusion, I've got my sample space, right, and I've got A and B happening like this, right? They don't interact at all. So their intersection is the null set. The probability of this intersection happening is 0, right? So I can say the probability of A intersect B is equal to 0. It doesn't happen. They don't overlap at all, okay? So in an independent event, right, I can think about, I've got A and B actually both occurring, right? So the probability of A intersect B is greater than 0 because they do actually both occur, but one doesn't influence the other, okay? Hang on, let me move this stuff out of the way so I can see my screen better. But it's a good question. They're similar, right? In terms of the fact that, like in mutual exclusion, A doesn't influence B, B doesn't influence A. And the same thing is true when I have two independent events. They're not influencing, the probabilities aren't influencing each other at all. Okay, it's not conditional in any way, but the intersection is non-zero. And that's an important thing because they're both actually happening. Let's see, do I have somebody here? No? Okay, all right. Okay, so let's go. Does that answer your question?
Yeah. Thank you.
It's kind of a fine-tuned question, but you're right. They're similar in concept, right? In that they don't influence each other. But in an independent event, they do actually have a case where they're going to be overlap. We want to see the case where both is occurring. So both are occurring, right, at the same time, because I've got two independent events that are happening. Like I'm flipping a coin and I'm rolling a die. Those are two independent events that are happening within my sample space, and I want to see what's the probability of this outcome, you know, and this outcome happening at the same time. So let's finish doing this here, and then we'll come back if you guys have other questions still. Give me just a second. Okay, so I've got the sample space for our coin toss. Sorry, right down. This is our coin. Sorry, coin toss is our head tail. And then I'm going to write the sample space for our die. It's a 6-sided die, remember. 1, 2, 3, 4, 5, 6. Okay. You can assume it's 6-sided unless we tell you otherwise. So I want to say the probability of a head and a 4 happening. Okay. It's going to be equal to the probability of a head times the probability of a 4. Okay. So now the probability of a head happening, right? It's a 1 out of 2. We're assuming these things are fair die and fair coins. So this is 1 out of 2. The probability of a 4 happening is 1 out of 6. 1 out of 12, which is approximately equal to 0.083. Let's take a step back. I'm going to enumerate the whole sample space, right? The whole sample space that we can get. So if I toss a head, and I get a 1, and I toss a head, and I get a 2. Like this is my die. This is my coin toss. This is my die. Head 3, head 4, head 5, head 6. I can get a tail 1, tail 2, tail 3, tail 4, tail 5, tail 6. Okay, so I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 possible outcomes. Okay, and we're looking for a head and a 4, right? So I have one possibility out of 12, right? So that's where this is coming from right here, one possibility out of 12. What we're seeing now, instead of me just telling you, well, the intersection of head and 4 is 112, let's calculate the rest of it, okay? We're actually calculating out what's the probability of heads, the probability of the die roll, and then we're seeing, because they're independent events, I can multiply those two probabilities together. Okay, example 2, right? So example 2 is, let's move this up here. Actually, do you guys all have this? Can't tell if anybody's still writing. Okay, so example 2, right? We're drawing a card from a deck, okay, and then we're replacing it, okay? Taking a card out and I'm replacing it. So then a second card is drawn. We want to find the probability of getting a king and then a 7. Okay, so now what's happening is because I'm replacing it, it's as though each event that was happening, taking each card out of the deck, isn't related to what's happened before, okay? Because I'm replacing the card back. So it's like I'm starting over from scratch again. Okay, so let's enumerate. We've got a deck of cards. So a deck has 52 cards, okay? And then the number of kings that we have, right? We have 1 king per suit. We've got 4 suits. So the number of kings total is 4. Number of 7s, right? I've got 1 7 in each suit, which means I have 4 7s total, okay? And then I want to be able to say the probability of a king is equal to 4 out of 52. I've got 4 cards in my king subset, and I've got 52 cards total. The probability of a 7 happening, right, is 4 out of 52, okay? So now I want to take a look at what's the probability of a king on the first draw and then a 7 on the second draw. I'm just going to write king 1, 7, 2, just so we know we're talking about pulling a card out, putting it back, taking another card out. I can really just say a king and a 7, right? But I'm just kind of enumerating it that way. So that's equal to, because these are independent events, I'm replacing the cards. It's like I'm starting from scratch each time. This is the probability of a king times the probability of a 7. Okay, we're going to plug it in. 4 to 52, 4 to 52. Okay, I'm just going to multiply through, which is approximately equal to 0.006. Okay. So I have 2 draws, 2 events that are happening. They're not affecting the outcome of the one that happened before or after it. So they're independent events. Okay. All right. All right. So now let's do the deck of cards again, but let's take a look at, we're going to we're going to draw a king from a deck of cards, right? And event B, that's event A. Event B is defined as drawing a diamond. So it's possible, right? I can have a king of diamonds, okay? So we want to be able to find out what's the probability of drawing a king of diamonds, right? Because that's actually a possibility where those 2 types of events are going to overlap. So let's again think about it. So I want to say the probability of a king and a diamond is going to equal to the probability of a king times the probability of a diamond, okay? So let's go back to the number of diamonds in our deck of cards, okay? So a diamond is a suit, right? We have 13 cards of each suit, right? So I've got 13 diamonds that are possible. We already said before in our previous example, I've got 4 kings. Okay, so I'm going to put these together. So the probability of king and a diamond is going to be, right? The king is going to be 4 out of 52. The diamond is 13 out of 52. Right, I'm multiplying those 2 probabilities together. Now I'm going to get 13 times 4. That's 52. 52 squared, which is 1 out of 52. Which we only have 1 king of diamond in our deck of cards, which is approximately equal to 0.0192. Okay. Kind of seeing where we're coming from. So this is like how we've been working at, how we've been thinking about it intuitively up until this point too. Okay. Right. Example 4. Give me a sec. Get this in the right spot. So example 4 says we've got a bucket. Now we have a lot of examples with like buckets and things where we take things out and do stuff with them. So we've got a bucket and it has 2 red balls, has 5 blue balls and 3 white balls. Okay, so let me just quick draw a picture. So I've got a bucket, I've got 2 red balls, 5 blue balls, and 3 white balls. Okay, helps to kind of visualize what's happening. We're going to take a ball out of this bucket. We're going to look at what it is. We're going to write it down, and then we're going to put the ball back. Okay, back to the bucket, and then we're going to, do other things. By the very fact that I'm putting the ball back into the bucket each time means each time I select something out of that bucket, it's as though I were starting from scratch at the very beginning each time. Okay, if I were to take one out, leave it out, and take something out, you can see how that's going to change the probabilities, because the overall quantity, right, I've got 10 balls total in this bucket, right? But because I'm returning the balls back to the bucket each time, my overall probabilities don't change every time I do it. So each time I dip in and take a ball out, it's as though I were starting all over again, which means each event is going to be independent. So that's how you want to be thinking about it. Okay, so let's find the probability of each. Part A is selecting 3 blue balls with replacement. We're kind of enumerating that we're replacing everything. We're going to select 1 white ball and then 1 red ball, but we're replacing it each time. Selecting 2 blue balls and then 1 white ball. But remember, we're looking at the color and we're putting the ball back. It's not like what we did yesterday, where I took a ball out and then I had to enumerate each path, right? And this is what I got. Like, this was the sequence of events that I was getting, okay, because the probabilities changed each time. Okay, so let's work it through. So part A says we're going to select 3 blue balls, okay? So I need to think about what's the probability. I'll write it down over here. So the probability of getting a blue ball, right? So I've got 10 balls total, and I have 5 blue balls. So I've got 5 out of 10 is my probability of getting a blue ball. Probability of getting a red ball, I've got 2 red balls out of 10. And the probability of getting a white ball, I've got 3 white balls out of 10. Okay, right? So I want to get 3 blue balls total. So I'm looking at the probability of blue, and then a blue, and then a blue, okay? Which is going to be the probability of blue times blue times blue, okay? Because each one is independent, the probabilities don't change. I'm not going along some path, a tree path. I'm looking at this bucket brand new each time that I'm working on it. So this is 5 out of 10, 5 out of 10, 5 out of 10. Okay, 120, you can simplify these if you want to just left them as whole numbers so we can see what the probabilities are more easily. 125 over 1,000, which is 0.125. Okay, that's the probability of 3 independent events, the outcome of which is blue each time. Okay. B, part B is say we're going to select 1 white ball, then 1 red ball. Okay, that's what we're trying to do. So you can say the probability of a white and then a red. Okay, which, because they're independent, it's white times red. Okay, so I'm going to plug in what I have. So the probability of white, like we said before, 3 out of 10, times the probability of red, 2 out of 10, 6 out of 100, which gives us 0.06. Okay, getting a white and then a red on each independent trial. Okay. Part C says we want to select 2 blue balls and then 1 white ball. Okay, so I'm looking at the probability of blue, blue, white. Okay, now I want to look at blue, blue, white. Okay, all right, so this is 5 out of 10, 5 out of 10, 3 out of 10. Oops, sorry, I'm writing it wrong. 75, 1,000. Okay, which gives us that. Get this off my screen. These windows are driving me crazy. Move this so I can see. Okay, all right. Make sure you guys have that written down. Okay. I know maybe you're sitting there waiting for me to start. I can't see if anybody's still writing, so I'm just going to give it a second or a few, and then let you guys finish writing it. Okay, so let's talk about independence of events and the complements of those independence. Okay, so let's say, suppose A and B are independent. Okay. The question that we want to ask is, are A complement and B complement also independent? Okay, we want to make that assumption. We want to find out if that's going to be true. I'll tell you the answer, and then we'll talk about why. So the answer is yes. A complement and B complement are also independent. Okay. So we can say that the union of two complements is the complement of their intersection. Okay, we'll draw pictures so you can see. I'll use some colors too. Okay, and then we'll talk about why that is. So let me just draw our quick sample space. Let's do this. Okay, here's A. Right, this here is A. I'll write it like that. And then I'll draw B. There's B happening. Okay. Now, outside of this out here, we're going to write do for A complement. So A complement. Wait, there's a little delay on the video here. A complement is everything outside of A. So I'm going to start drawing it in. So it goes like this, including this bit of B that doesn't intersect with A. That's all part of A complement. And then, looking for different colored pens here. Okay, so then B complement, right, is everything outside of B, including this bit of A. So I'll try to draw it with different hash marks this way. So we're going this way. Okay, so that's B complement. It includes this part of A that doesn't intersect with B. So now the only part that's not actually shaded in, it's hard to see because we shaded it in with A and B. This is the only part that's not shaded. It's the part where they're intersecting each other. Okay, so let's talk about, this is sort of our picture here. Right there, this is A intersect B, that part, and this is our sample space. Okay, so let's talk about why, right? So we want to be able to go through the proof on why. So you can see also, I'm belaboring the point on the proof so that you can also see how we're manipulating our probabilities and the logic that we use, because you can use this logic when you're answering like homework questions and test questions too. Okay, so let's talk about it. We're looking at the probability of A complement union B complement. Okay, so I'm going to start taking putting things together. So A complement union B complement is going to be the probability of A complement plus the probability of B complement minus the probability of A complement intersect B complement. Okay, and that comes from here. Okay, where these two intersect, I'm going to subtract them so I don't double count them, right? Because A complement and B complement are going to be overlapping each other, and so we want to take out those double counting. So this is going to equal to 1 minus the probability of A intersect B. Okay, because basically, remember how we did it on the graph? 1, because this is our sample space, probability of our sample space is equal to 1, right? This whole thing, right, this union here, is everything except where A and B are intersecting each other. So this is 1 minus the probability of A intersect B. Okay, so keep that in mind. So I'm going to start working things around. So I'm going to say 1 minus the probability of A intersect B is equal to 1 minus the probability of A. That's my A complement, right? Plus 1 minus the probability of B. That's my B complement. Oops, that should be a P. Probability of B. Okay, that's my B complement. Minus the probability of A complement intersect B complement. That's just writing it down in place here. Okay, so A and B are independent. That was defined at the beginning. We were told that A and B were independent events. Okay, so we're looking at their complement. So A and B are independent. So what that means is probability of A intersect B is equal to the probability of A times the probability of B. So I'm going to exploit that in my equation here. Okay, so I'm going to put this in. Probability of A complement intersect B complement is equal to 1 minus the probability of A plus 1 minus the probability of B minus 1 minus the probability of A times the probability of B. Okay, so I just took out the parentheses on these two terms, right? And I substituted in here, this bit right here, I substituted in here this, okay? And then for here, I substituted in probability of A times the probability of B. Okay, so that's all we're doing is substitution. Okay, so I'm just gonna get rid of the parentheses. I'm gonna distribute the negative. So I'm gonna get 1 minus plus 1 minus P of B minus 1 plus P of A times P of B. Right, one of these ones cancel out, so I get 1 minus P of A minus, oops, sorry, can't see the screen, sorry about that. Probability of B of, oops, that's a B, plus P of A times P of B. Okay, it's hard to see this actually, but this is like a quadratic equation that's been distributed, been FOILed out. So I'm going to put it back into its two factors, 1 minus P of A times 1 minus P of B. You can see that if I were to FOIL this out, I get 1 minus P of B minus P of A plus P of A times P of B. It's not exactly obvious. We're used to, and this doesn't look very good. This is a P of B. We're used to thinking things in terms of like x squared, you know, 2ab, all that kind of stuff, and b squared. But now, right, if you want to prove to yourself, you can FOIL these out and see that that's actually the case. So 1 minus P of A, this is probability of A complement. 1 minus P of B is probability of B complement. Okay, so we've just shown, right, that the probability of A complement intersect B complement is equal to the probabilities of those two complements multiplied together. Okay, so we can conclude if A and B are independent, then A complement and B complement are also independent. Many times I'll leave the proofs to the book, but I think, you know, in this case here, the proofs really help you because they help you see like how we can manipulate the probabilities and how I can substitute and how I can combine them and what it means to actually work with it. Because these are the type of algebra, right, that you're going to be needing to do on like homework problems and stuff. And to know that you can actually manipulate probabilities as though they were a variable in an equation like we did here, okay, putting things together. So quick question, you asked about mutual exclusion. I'm just going to write it down here so that it's in our notes specifically because we want to talk about mutual exclusion. So we want to say, does mutual exclusion imply independence? Right? They seem like they should be related, okay? And they're only related in the fact that A and B aren't influencing each other. So the answer is no, because if A and B are mutually exclusive, this is what we said before, mutually exclusive, then the probability of their intersection is equal to 0, right? Because they don't intersect at all, like they're not happening together, right? And so there's no intersection, so the probability of their intersection is 0. And then we know that the probability when they're independent the probability of A intersect B is equal to the probability of A times the probability of B, right, which is non-zero. It's going to be equal to some value, okay? So that means that this equality here is not met when they're independent, okay? We want this to be greater than 0 because they're actually two events that are happening in the same sample space, but they're not, you know, affecting one another, okay? Okay, so let's think about, I'm going to use the word mutual again, but it's not in terms of mutual exclusion, but we'll call it mutual independence. So mutual independence of more than two events, right? So I'm now going to be thinking, we've just talked about two events, A and B happening. Let's say I have A, B, C, and so on and so forth, right? But they're all happening within the same experimental space or in the same sample space, but they're not affecting one another. Okay, so we would say that they are mutually independent, okay? And I've got multiple events that are happening in that sample space. So we'll call this mutual independence. We're going to say events, I'm just going to define it in terms of math. So events A1, A2, A3, oh, so on and so forth, all the way up to some, number, A sub n. And we're going to call them independent if the probability of all of their intersections, so A1 intersect A2, intersect A3, intersect all the way up to A sub n, okay, if that's equal to the probability, the product of their probabilities. So what this is also saying is, this is also a check, right? If I give you the probability of the intersection and you find somehow, or you're given the individual probabilities, right? If you multiply those probabilities together and it's equal to the probability of their intersection, you can then conclude that A and B are independent of one another, okay? So sometimes we'll tell you these two events are independent, or you'll be able to deduce based on the problem, about what's happening. More often than not, especially when we get into the statistics section, we're going to tell you these are independent events. But often we're going to ask you, these things are happening, here are the probabilities. Go do some algebra, come back and tell me, are these two events independent of one another? Okay, and you're going to do that by checking. I'm going to check the probability of their intersection with the product of their individual probabilities. If those two are the same, then I can then conclude that these two events are independent of one another, or three events or four events or whatever are all mutually independent, okay? So it's a good check to see if something's independent, in addition to being able to calculate stuff if you're told ahead of time that they are, okay? So I'm gonna go back, we have another example. I'm gonna go back to my example sheet. Example 5. We have, it says an insurance company. Okay, so you've got, sorry, let me put this on the page. An insurance company wants to assess the future liabilities of 3 clients. Each of these clients are from vastly different states. So one's in Alaska, one's in Missouri, one's in Vermont. We're gonna assume that these people are not related to each other, okay? That there's no, that they didn't grow up together, that they are completely independent of one another, right? So, and we're gonna say that each person, because this is an insurance company, each person has the following chances, this is the probability, chances of survival over the next 5 years. Probability of A, that's our Alaska person, has a 0.7, 70% chance of survival. M, probability of Missouri, has a 90% chance of survival, okay? Probability of V, okay, Vermont person, has a 30% chance of survival over the next 5 years, okay? So what we want to do is find out what's the probability that by the end of the 5 years, the insurance company will have to pay death benefits to exactly one of these 3 people, okay? All right, so let's start enumerating what we have and what we need to think about and how we're going to do this, okay? So I'm going to write down different probabilities. So I'm going to say the probability that my Alaska person dies, because we're talking about death benefits, which is going to be, this is just Alaska now, because they say exactly one person. So I'm going to look at the complement of Alaska. So this, what they gave us before was the probability that they'll survive. And I want its complement, because that's the probability that they won't survive. So a complement says that they're going to pass away, but Missouri and Vermont, this is a V. So Alaska dies, but Missouri and Vermont are still around, okay? And I'm going to write down, let's just write it up here. So I'm going to say my Alaska complement is 1 minus, that's right, probability of Alaska complement is 1 minus the probability of Alaska. And then I'll write my Missouri complement is 1 minus the probability of Missouri. And then the same thing, the probability of Vermont complement is 1 minus the probability of Vermont. We'll just fill those out ahead of time, okay? So we're going to do that for the other cases, right? Because this is just for where Alaska dies. So the probability that only Missouri person passes away. So now Alaska is still alive, but the Missouri, our complement, right, they've passed away, and Vermont is still around. Probability that Vermont only, probability that Alaska, Missouri are still alive, but Vermont has passed away, okay? So they didn't ask, let's do where, at least one or whatever. We're just talking about exactly one. So that's why we're just doing, Alaska only, Missouri only, and Vermont only. Okay. So exactly one person dies is the union of all three of these possibilities right here. So we're going to put that. So I'm going to say that this is the probability of, let's see, AC, M, B, union, A, MC, B, union, A, M, B, C. And, okay, so the probability of this one and this one and this one is the probability that exactly one person dies. Because I have to take into account, is it Alaska or Missouri or Vermont, right? So this is how we're dealing with that, okay? So let's fill in the blanks, okay? So I'm gonna go, this is the probability of AC intersect M intersect V plus the probability of A, M, B plus the probability of A, M, B, C, okay? And then I'm just gonna write it. So I'm gonna make the assumption all three people are independent. When we talk, especially in the statistics section, the assumptions become important, right? We're going to say when we're doing some statistical analysis on a bunch of underlying data we have to say is independent. We're going to assume that the underlying data is independent. Okay, we do as much as we can in experimentation to make sure that the underlying data is going to be independent because we don't want it to influence the outcome. So we're going to make that assumption unless otherwise stated. Okay, so let's start filling in the blanks on how we work it through. So I'm going to say because of this, right, and these events are independent, so I'm going to fill in the blanks. Probability of AC times the probability of Missouri times the probability of Vermont, plus, again, we're going to fill in this, Alaska, Missouri complement, Vermont, plus Alaska, Missouri, Vermont complement. Okay, so this set of three comes from here. This set of three comes from here, this intersection, right? This set of three products comes from here, this intersection. Okay, we just substituted based on the fact that our assumption says all three of these people are independent. Okay. Now I can start filling in numbers, right? Because we were given numbers at the beginning, which is the probability of survival for each of these three. And we said the probability of passing away is going to be 1 minus the probability of survival. So we've got our probability, our complements already. So let's fill in the blanks based on what we have, and then we'll start multiplying. So A complement 1 minus 0.7, Missouri survival, Vermont survival, plus A 0.7, 1 minus 0.9, 0.3, plus 0.7, 0.9, and 1 minus 0.3. Okay, so I just filled in the blanks based on the numbers that we had. Okay, multiply it all the way through, and I got 0.543. Okay, so that's the probability that within the end of the 5 years, the insurance company is going to have to pay death benefits to exactly one of these three people. It's about a 50%, 54% chance that's going to happen. Okay, given the survival rates that were assessed. I'll let you guys finish writing that. Okay. Right? Okay, last one. Let's do this. We may need an extra page when I do this problem out. Actually, needed more space on here, but so I can be prepared to roll over onto another piece of paper. All right. So the game of craps is something that I learned when I started teaching probability and statistics. So I'm going to work with the rules that are given to me by by our particular book. So we've got 2 dice, right? We're rolling, okay? So we're gonna win, right? If we get a sum of the 2 faces, sum is 4, 5, 6, 8, 9, or 10. We have to get that sum twice before rolling a sum of 7. Okay, so that's how we're gonna win. So I can get a 4 and a 4 and then a 7, and then I win, okay? If I get a 4, a 5, and a 7, I lose because I don't get 2 4s in a row. That first thing that I roll, that first sum that I get is the point that I'm looking for. Okay, I'm looking for a repeat of that sum, okay, before I get to a sum of 7. So we want to find out what's the probability that a player wins with a point of 10, right? So this is all these different possibilities. We want to know what it is with 10, okay? So let's think about, I'll write down what our winning round looks like as an example, and then we'll talk about it. So let's just do this. So example, a particular, not this particular, but a particular winning round is going to look like if I roll a 6, sorry, I roll a 6 on the first one, and then that's my sum of the 2 die faces. I get a 5, an 8, an 8, and then I get another 6, and then I get a 7. See how I've gotten 2 6s, right, before I rolled the 7, so then the point that I get is equal to a 6. Okay. Our losing round, okay, let's say I roll an 8. So 8 is going to be the point that I'm looking for. I want a repeat of 8 before I roll a 7. I roll an 8, and then I roll a 4, and then I roll a 10. Oh no, I got a 7. So I didn't get an 8, right? We'll write this out. We rolled a 7 before we rolled an 8. So therefore we lose, okay? We didn't get the 8 in time before it came up 7s. Okay, so we want to find out what's the probability that a player wins with a point of 10. Now remember, on that first day, we enumerated out that whole sample space, right? I had die 2, die 1, and I had these little ordered pairs of, this is the face value for each one. We're going to sum up those ordered pairs. I'm not going to write out that whole sample space. We're going to talk about it in terms of what we're trying to do, okay? But that's the sample space that you should be picturing in your mind, or you can get it out of your notes and take a look at, because it's going to help you a lot in answering questions like this. Okay, so we've got 2 dice, and we're going to assume that they're fair, 6-sided. Okay, so the total number of possible combinations, remember from that table, is 36. Okay, so I've got 2 6-sided fair die. The total possible combinations that I can get for each of their faces and the rolls that I'm doing is 36. Okay, and we're going to make the assumption that each roll is independent. Right, it makes sense. I've got this, I'm rolling it. I've got this, I'm rolling it. Each event that's happening is not related to the time before. Okay, we're going to make that assumption. Each roll is independent. Okay, so now because we're dealing with, the question says we're going to look for a point of 10. So I need to say, how many ways can we sum up to 10? Okay, so I'm going to enumerate these out just so we can see what they look like. So I can go a 4 and a 6. I can go 5 and a 5, and a 6 and a 4. So in my sample space for rolling up to a sum of 10, I only have 3 possibilities. Okay. Now the number of ways to sum to a 7, let's enumerate those out. Okay, so I've got a 6 and a 1. Oh, I've got a 5 and a 2, a 4 and a 3, a 3 and a 4, a 2 and a 5, oops, and a 1 and a 6. Sorry, just 1 and a 6. Okay, so I've got 1, 2, 3, 4, 5, 6. Ooh, 6 different. So already I'm looking like 7 happens. The possibilities, the ways to roll up to 7, I have more possibilities than I have to roll up to 10. So you can kind of see how the game of craps, right, that the ways to lose, okay, it looks like the ways to lose maybe, we're going to calculate out the whole table, but the ways to lose, at least in this case, outnumber the ways to win with a point of 10, okay? So let's think about this one. We want to be able to find, let's see, I'm going to take 3 and 6. So I'm going to go, we're going to write down what that means. 3 plus 6, this is 9. This is, I want to subtract this from 36, because what this is going to do is it's going to help me to find the number of ways not to sum to 7 or 10, right? the reason I'm doing that, that goes back to our beginning, right? Remember at the very beginning, we're talking about an example of a winning round. So I'm rolling a 6, and I'm looking at these are the number of ways that I can roll not a 6 or not a 7, right? So if I subtract these possible combinations, rolling up to a 6 or rolling up to a 7 from the total number of possibilities, that'll help me count all the different possible ways, combinations that I can get to sum up to numbers other than the point that I'm looking for, which is 10, and the point that's going to cause me to lose the game, which is 7. Okay, so when I do this, so 36 minus 9 is equal to 27. So 27 is the particular number that we need, right? Because I've got 3 ways to sum to 10 and 6 ways to sum to 7. So all the possible combinations minus these 9 things that I'm looking for are 27. Okay, so keep that number in mind, the 27. Okay, so let's enumerate out what our possibilities are. And we're going to start enumerating these things out, and then we're going to talk about formalizing them. So, okay, so this is our sequence of rolls. And then we've got a probability of each roll. Okay, and I've got a table here that's happening. So I can get a 10 and a 10. Okay, the probability of getting a 10 and 10. Now before we just said that the number of ways to sum to a 10 is 3, right? And I've got 36 possible ways that I can do that. So the probability of rolling a 10 and then a 10 is 3 out of 36 and 3 out of 36. Okay. So now I'm going to roll a 10, no 7, no 10, and then a 10. Okay. This is, I'm going to keep building things up. So 10, no 7, no 10, and 10. I think maybe we have like a homework problem like this, if I remember, something similar. Okay, so I'm going to get 3 out of 36. That counts for my first 10. This, we just said, was 27 possibilities not to get a 7 or not to get a 10. And then again, my 10 at the end. Okay. We're going to do it again. So I'll do a couple, and then we're going to start talking about no 7, no 10, no 7, no 10, and then a 10. Right, so I'm rolling it 1, 2, 3, 4 times. I get a 10 on the first one, not a 7, not a 10, not a 7, not a 10, and then I get a 10. Okay, so I'm going to count this. So 3 out of 36 times. This is my first, no 7 or 10. This is my second, no 7 or 10. And this is my last 10. This is the point that I'm getting. I'm going to generalize with a dot, dot, dot. So I'm going to get a 10 on my first roll. I'm going to get no 7, no 10. I'm going to get a whole bunch of no 7s, no 10s. And then I'm going to get a 10. Okay, so this is like, I've got like a whole bunch of, maybe possibly even an infinite number. It's possible, but probably unlikely. All right, so 3 out of 36 times 27 out of 36 times so many 27s out of 36s times 3 out of 10. Okay, so this is the part here that we're going to start thinking about how do we generalize, right? This sequence, right, can go on forever, and we can go on and on and on. Okay, so it's the sum, you know, all these different things, because I could have, this is my first roll, I could have this one or this one or this one or this one. So I'm going to be summing up all of these, okay? So let's write this down. So I'm going to say sequences are right. All these sequences are mutually exclusive because each one happens. Like this is a possibility, then this is a possibility, or this is a possibility, or this is a possibility. I'm not going to get this and this happening, okay? So each of these sequences are mutually exclusive. So that means that the probability of winning, oh, sorry, you can't say that, probability of winning a point of 10 is the sum of basically an infinite number of products. The products are here, the possibility of each roll. Each of these events here are independent, or right, independent.
Why did you multiply by 3/10?
Oh, sorry, because I made a mistake, sorry. I was thinking 10, so 36, thank you.
No problem.
It was a point of 10, right? That's where the 10 came. It was a mistake. 36. Good, thank you. Right, so all the sequences are mutually exclusive. I could have this one, or I could have this, or I could have this, or I could have this. So because each of these is possible, I have to sum them all up. But there's an infinite number of possibilities, right? We can end up rolling forever. And how am I going to do this? So let's see, I'm going to get out my second page here. This is, I'm moving on to a second page here. So let's write down, right? We're summing up things. Let's do it like this so you can start to see things together. Okay, I'm summing up, right, these products here. Okay, I've got an infinite, this is an infinite sum. Okay, so let's talk about what an infinite sum looks like. Okay, so this is that the probability that a player wins with a point of 10 is going to equal to, I'm going to add these up, so 3 out of 36, 3 out of 36, plus, this is my next roll on here, 3 out of 36 times 27 out of 36 times 3 out of 36, right? Plus 3, 36 times 27, 36 times 27, 36 times 3 out of 36, and so on and so forth, right? So I've got this, it's sandwiched between two constant terms, right? So I've got a constant term, 3 out of, sorry, you can't see that, 3 out of 36 times 3 out of 36, right? It's sandwiched between these two here. And then I'm basically, I've got this 27 out of 36 that's happening, well, geez, on my, let's go back to here to our table. I'm spending a lot of time on this because, and I'll tell you why in a minute. Right, so this is my first roll, and I don't have any 27 out of 36. This is my, I can count this, maybe I'll count this as my 0th roll. This is my first roll. I've got 1 27 out of 36. Let's say this is my second roll. I've got 2 27 out of 36s. On my third roll, I'm going to have 3 27 out of 36s. You can see where I'm going with this. Right, there's a pattern that's building up. Okay, so where k basically, it starts at 0 and it goes up to potentially infinity, right? It's essentially whatever roll you're on to make that point. Okay, and because we're summing these things up, right? So our probability is equal to the sum, k equals 0 to infinity, 3 out of 36 times 3 out of 36. I'll put parentheses around that just so you can know that that is a constant term, times 27 out of 36 to the kth power, okay? This is our probability that a player wins with a point 10, okay? So, let's see this, I wrote this constant term is here. Sorry, that's this term here. The reason I'm belaboring this point is, I recognize some of you from my Calculus 2 classes. We often talk about our series, right? And everybody says, when are we ever going to use these series again, right? If you remember from your Calculus 2, we talked about the different series types and building up that table of how do I recognize different series types. I have a constant term times a number, right? That's raised to a particular power. That power is my index, which in this case starts at 0 and goes up to infinity, okay? So when we think about this, I'm going to write this again so maybe you'll see it. This is equal to k equals 0 to infinity. I've got a as my constant term, r to the k, okay? Where this, if you'll recognize it, is a geometric series, okay? Now remember, our criteria for a geometric series converging is that our r, the absolute value of our r, has to be between 0 and 1, has to be a fraction. 27 out of 36, right, is between 0 and 1. We take its absolute value. In this case, it's positive. Okay, so that means that this is going to converge. And luckily, because it converges, it means that we can calculate its sum. So the sum of a geometric series, remember, is a over 1 minus r. Okay, now we don't have to subtract out a 0th term or anything because we're starting at 0 here. Okay, so I'm going to set this up. So if I say, let's go like this, r equals 27 out of 36, and my a is 3 out of 36 times 3 out of 36. Okay, so I'm going to plug these into this equation here. So I'm going to get the sum is equal to 3, 36, 3, 36, all over 1 minus 27 out of 36. Sorry, you can't see that. This is our formula for the sum of a geometric series. That's where I'm getting this from. Okay, so I worked this through, okay, did a bunch of math, and basically it comes out to be 1 out of 36. I'm skipping how all that math works. Okay, so this is the probability that a player wins with a point of 10. This was just for 10, right? Now they could win with a point of 2, 3, 4, 5, 6, not 7, 8, 9, or 10, right? I mean, there are all these different possibilities that we can win with a point of, okay? So we're going to go through and we're going to take a look at what are all the possible sums. Like we would do this whole math and calculate all these probabilities for all the possible winning points. And we were able to build up a table. This is actually going to lead into different topics that we're going to talk about as we go along in the semester. Okay, so let's do this. So we're going to do this math for all the numbers in the winning point category. Okay, so that means that a player, one of the rules is that the player is going to win by rolling a sum of 7 or 11 on the first roll, only on the first roll. Okay, or the player is going to win by getting a 4, 5, 6, 8, 9, or 10 on the first roll, and then what we call making the point, which is what we've just been calculating. Okay, so they roll, they roll, they roll. Hopefully they get that next sum, the same sum again, before they get a 7. Okay, so let's build up a table. I'm going to build up a table where we do this for all the different possible points and what the probabilities are. Okay, I'm going to put this over here. I'll scan this in and then put this up online. So in case I'm going kind of fast on this, you'll be able to see it probably after lecture or after office hours, depending on when I can get to it. All right, so point. And then the probability that the player makes the point. So we're going to make a table, right? So the point of 4. Now, all that work that we just did building up the probability for point of 10, I've been doing for all these different points. Okay, so for 4, it's going to be 1 out of 36. For 5, it's 16 out of 360. For 6, it's 25 out of 396. For 8, it's 25 out of 396. For 9, it's 16 out of 360. And then for 10, it's 1 out of 36. And then we'll put off to the side the probability of getting a 7, because I can win if I get a 7 on the first roll. It's going to be 6 out of 36. Remember, there were 6 combinations of summing up to 7. That's how we get to this. The probability of getting to an 11 is 2 out of 36. There are only 2 possible ways for 2 dice to sum up to 11. That's where these numerator numbers are coming from. Okay, so using this table here, we'll say that the probability that a player wins, right, by getting any particular point out of here, which is the sum of all the possibilities, okay, it's going to equal to 6 out of 36 plus 2 out of 36. This is getting a 7 or an 11 on the first roll. Plus, I'm going to sum up all of this whole column here. 1 out of 36 plus 16 out of 360 plus 25 out of 396 plus 25, 396 plus 16 out of 360 plus 1 out of 36, right? So you can see where these numbers came from. I summed up the whole table, right? Plus the probability of 7 and 11, because it's all the different possibilities. I can get a win with these different ways, okay? So I do it all out and I get 0.493, right? So this means that a player has about a 50% chance of winning, okay? I guess it's fair. right? It's not biased in favor of the player, okay? And it's not necessarily biased against the player, right? You've got about a 50% chance of winning in a game of craps, okay? So that's the end of chapter 2.5. I'll leave this up here for a second if you're still writing. So we have some time. We've got, maybe about 20 minutes, 25 minutes or so, or a little bit more if you guys want to ask questions about the homework. If you don't have any questions about the homework, you're free to go. And then we can talk in office hours or not, either way. Like I said, keep a look for the announcement where I'll talk about how we take the quiz, the logistics of how that's going to work, and what you need to do in terms of uploading and all that, okay? All right. So let me get out my homework problems. Does anybody have any questions on the homework problems that you want to ask while we're here?
Somebody wants you to explain 2.4.34.
Oh, okay. You have the chat line open. I can't see it. Let's see. Chat. Let me get up that window. 2.3.34. Will you be able to go to 2.4.31? Sure. Give me a sec. I just brought up the chat window. 34. Okay. Give me make a second for everybody to get that, and then I'll bring this up. Let me read the problem.
Professor, is the quiz
Yes,
from
this is a
2.2
great
to
question.
2.4?
I'm sorry?
Is the quiz from 2.2 to 2.4?
The quiz is going to be including 2.5. So all the stuff that you're passing in, okay, for your homework is going to include 2.5. So 2.2 to 2.5. So basically, when we take our quizzes, it's going to encompass the homework set, okay? And I realize that we've just covered 2.5, and that's essentially due tonight. I probably won't wait 2.5 as heavily on the quiz because you haven't had as much time to actually work on it, and so we can think about that. Actually, let me think about that, how we want to do that one. I may take 2. Let me think about that one if I want to take 2. I was going to include it because we're actually covering it today. Let me think about that one. Okay, sorry, let me cover 2.4.34. Okay, so this is a funky problem because to answer it fully, we actually need material that we haven't had already. Let me see. Let me get a pencil. Okay. So let me get out my solutions here. It'll be easier for me to explain. So there are 2 ways to think about it. One is a way that doesn't include all the details, and one way that does. So let's do 2.4.34. Okay, see there. Can you guys see that? Okay, that's in I'm shifting to pencil because I'm going to be calculating. So in this one, we have 40 red chips and 60 white chips. Okay, and we're taking these out of a bucket. We're taking 6 chips out, and we're tossing them. And then we're taking a 7th chip out. Excuse me. We want to find out what's the probability of getting a red on that 7th chip. And this is a 7. Okay. So the way I'm going to explain it simply first, based on what we know so far, and then I'll talk about a detailed solution that goes into material from chapter 2.6, which you technically haven't had yet, but which will actually make more sense probably when we talk about this. So let's just say when I take these 6 chips out, right, and I toss them, and I don't even look at them, right? So they have no bearing whatsoever on what I'm trying to do. Okay, and then I take a 7th chip out. It's as though I don't know, what's happening with these 6 chips. So I'm going to pretend that all I did was reduce the quantity, okay, but the proportion of reds and whites stayed the same. And so then I can say the probability of getting a red on here is the same thing as it would have been originally, which is 0.4. Okay, it's a slightly hand-wavy solution because we're not doing combinatorics, which is all the different ways that things can happen. Okay, but so that's given what we know so far. If we include combinatorics in our answer, okay? So what happens in combinatorics means I'm going to take 6 chips out, right? So I'm going to reduce the possibility. So I need to take into account all the different combinations. So I could have a case where I've got the probability of 0 reds and 6 whites that get taken out, right? So when I do this 0 red and 6 white, what happens at the end, my overall end distribution, right, is going to be, I've got the same number of reds as before, but I have still 6 less numbers of chips. So I've got 94 chips, right? So this is going to be, this is the probability of getting a red on the 7th chip. Now I need to take into account, if I'm taking out 0 reds and 6 whites, right, I have 60 to choose from, then 59 whites to choose from, then 58, 57, 56, 1, 2, 3, 4, 5, 55, right? All over, I have 100 chips, I've got 99 chips, I've got 98 chips, 97, 96, 95, okay? But now what happens is, I didn't give myself enough space here. Right, this is just one possible way. This means I took out a white chip on the first draw, a white chip on the second draw, whatever. But I could have different combinations of picking out a red chip. So I have to include 6, choose 0, because I'm taking out red chips this time. So 6, choose 0, we haven't talked about the combinatorics part yet, but 6, choose 0 is equal to 1. Okay, we're gonna actually cover combinatorics on Monday. And then this is multiplied by 40 over 94. Okay, and this is gonna give me a number, 0.17872. There's a lot of places to make mistakes on your calculator here. When I actually calculated these out, I needed to put it into an Excel spreadsheet so that the numbers were keeping track, so that they didn't go all over the place. So now that's the probability of taking 0 reds out. I've got 1 red, I've got 5 whites, I've got 2 reds, 4 whites, 3 reds, 3 whites. Oops, sorry, probability of 4 reds, 2 whites, probability of 5 reds, 1 white, and the probability of 6 reds and 0, so it would be white, 0 white. This, by the way, let me just specify, this answer here is totally fine, okay? I'm going overboard in explaining because it's actually, there's more detail to this problem, but given what we know so far, okay, the answer that we get when we do the combinatorics on here, okay, is actually, when I sum up all of these possibilities, the answer that I get is 0.4525, okay, which is close enough to 0.4 that we can then kind of hand wave, right, and say that the distribution is the same. This part here takes into account, so let me just write out a first couple here. So this is going to be, I've got 40, right, this is I've got 1 red that I'm choosing from, and then now I have 5 whites, this 60, 59, 58, 57, 56, 1, 2, 3, 4, 5. And then all of that is over the same thing, 100, all the way down to 95. Now in this case, I'm doing 6, choose 1, and I've got 1 red that I've taken out and thrown away, so this is 39 over 94, okay? So then these are gonna look like, this is 6, choose 2, and this is 38 over 94. This is 6, choose 3, 38, I'm sorry, 37. 94, because I've taken 1 of the reds, I've taken 3 of the reds out, 2 of the reds, so that my overall pool of reds changes. This is 6, choose 4, 36 over 94, 6, choose 5, 35 over 94, and 6, choose 6, and this is 34 over 94. Okay, so I'm not writing in all the numbers, but just so you can see, this includes combinatorics, right? Because did I choose the red on the first chip, or the red on the 5th chip, or the red on the whatever? So all of this gives us 0.4525, which for all intents and purposes for what we're trying to do in chapter 2.4 is, we're going to say it's equal to 0.4. It's enough, that close enough that we can hand wave our solution for chapter 2.4 because we haven't had combinatorics yet. But this is fine, right? To say that the distribution remains the same. This is a much more detailed explanation that you don't have to put down. I'm just showing you in case you were wondering why that was true. Okay, it's roughly true. This one doesn't take into account all the combinations. Okay, that's 2.4. Okay, so that's 2.4.34. All right, I can post the I'll post a detailed solution for 2.4.34 at a later point, just so you can see it. I hesitate to put that up there because it does include stuff that we haven't technically covered yet. It looks like somebody asked about 2.4.31, so let's see. Oh yeah, 3.1. So 3.1, why don't I do through one's actually a long problem. If you would like, let me write it out and do it, because it's like there's all these different things, and I'll scan it in and I'll post it, just because it's kind of like there's a lot of stuff that's going on, and I want to be able to explain it okay. We see question like 2.4.34 on the exam. Oh, sorry, the quiz. Yeah, you know, not like this. Okay, not with the combinatorics. So 2.4.34. The quiz is going to be, this is just to kind of get you to think about what happens when I take these 6 chips out, and then, you know, I don't know what they are, so I'm tossing them. It's the same distribution. This is overboard, right? We're not doing this on the quiz. Okay, the combinatorics part certainly. I think the quiz is probably it's probably more akin to the types of example problems that we've done in class. Okay, where you need to be calculating things out, you know, sort of algebraically and mathematically. This 3.4 is a little bit more hand wavy. And then problem 31, I'm gonna write up nicely, and then I'll post it. You know, probably write maybe like right before office hours, so that you guys can see it, and I'll put explanations in it, and then we can talk about it in office hours if you want. It's just kind of, there's a lot of stuff going on there. Anybody else? You guys are free to leave if you want to. You don't have to. You can say if you want to ask other questions, or you can think about it. Take a look at questions for the rest of the chapter sections. Take a look at, just even read through the questions for 2. And then we meet up again in about an hour. And then can I please see 2.2.46? Oh, sure. Let's see. 2.2. I don't have 4.6. Do you mean 2.6? 2.2.26? Oh, 2.4. All right. Sorry. Let me get it up. Oh yeah, this is another one. All right. All right. So. All right. So 2.4.46. All right. So this one says we've got the probability that the rat poison is fatal is equal to 0.6. Writing down different pieces that we have. Okay. And then we have the probability that the cyanide is fatal is equal to 0.9. Okay. And then the person has a 50% chance of eating the rat poison, 40% chance of eating cyanide, and then a 10% chance of not eating at all. Okay, so if there is a death, then was the death caused by rat poison, cyanide, or both? That's the question I want to talk about. So I'm going to say that my event B is the event of a death. Okay, I'm going to say event A1 is the event that rat poison was used. Event A2 is the event of cyanide. And event A3 is none. Okay, so I'm going to say the probability that event B given A1, right, that there was a death and it came by rat poison is equal to 0.6. Okay, so that's what we were told at the beginning. Probability that there was a death given that it was cyanide is equal to 0.9. And the probability, probability of event A3, B given A3 is equal to 0. Right, we're going to make the assumption that they don't eat at all, or that they're just dying from no causes. They're not going to die from that. Okay. So now we're going to say the probability of A1, right, with the event A1 happening is 0.5. This is the probability that they ate the rat poison, right? The probability of A2 is equal to 0.4. These are based on the chances that they gave us before. Probability of A3 is equal to 0.1. Okay. Now I'm going to say the probability of A1 given B, right? So they died, so was it A1? Okay. So this is the probability of A1 given B. We're going to write out our conditional probabilities. Probabilities is Bayes' rule, right? B given A1 times the probability of A1. Okay. And that's all over the probability of B given A1 times the probability of A1 plus the probability of B given A2 times the probability of A2. I'm running out of space here. Plus probability of B given A3 times the probability of A3. Okay, so we're working our way back. We're saying that they died, from rat poison, right? And then these are all the different ways that it can happen. So we're trying to work our way backwards. So I'm going to start filling in numbers. So this is 0.6, 0.5, all over 0.6, 0.5, plus 0.9, 0.4, plus 0 times 0.1. Okay, so we multiply all these out and we get 0.45. Okay, so that's the probability that the rat poison caused the death. Okay, so now let's do it again for the cyanide. So probability, so this means that they died, was it by cyanide? So we're going to go the probability that there's a death and it was caused by A2 times the probability of A2 all over. This is Bayes' rule again. So I'm going to go probability of B given A1 times the probability of A1, just like we did before, plus the probability of B given A2 times the probability of A2, plus the probability of B given A3 times the probability, I'm running out of space, A3. Okay, so I'll fill in the numbers. Sorry, can you see that? I'll fill in the numbers. So this is 0.9, 0.4, all over 0.6, 0.5, plus 0.9, 0.4. I'm not going to do the zeros anymore. And this one is equal to 0.36. Oh, sorry. Is equal to 0.54. Okay? This is 0.36. So the whole thing is equal to 0.54. So this has a higher probability than this one. So it's more likely cyanide has a higher probability. Of being the cause. That's all I wrote. Cyanide has a higher probability of being the cause of death. 0.54 from cyanide, 0.45 from rat poison, right? And so that's how we calculate it. It's Bayes' rule. Okay. Okay, and then keep your eyes peeled. I'll write up the other question that you asked for 3-1. I'll write that up and then post it today. This afternoon, I'll do it. Does anybody have another question? Otherwise, I'm gonna close out the meeting. And then if you guys want to come to office hours today to ask questions, that's I'll see you then.
Thank you.
Thanks. Take it easy, guys. I'm not seeing any other questions, so I'm just gonna